So I have found another critical value. Since I have seen the picture of my graph, I am expecting that my function should have a minimum there. Now, to actually check that this is a minimum, one thing that I can do is I can evaluate my derivative at coordinates to the left and to the right of this value. So it's going to be a little bit more obvious if I graph this. Here was my original function. And if I want the derivative of this, we calculated this in my previous video clip. And we got -2 divided by x cubed plus 6 divided by 10 minus x all cubed. And just to double check, Desmos can calculate that derivative for us. And hey, it's exactly the same picture. So notice that we have critical values anywhere this derivative is undefined or equal to 0. Where is it undefined? We've got a vertical asymptote here at x equals 10, a vertical asymptote here at x equals 0, and at x equals 10. And then we cross the x-axis pretty close to 4 here. Desmos is helpful and marks that with this gray dot at x coordinate 4.095. Well, I don't know the significance of 4.095. If you just give me a decimal expansion, I don't know what makes that number special. I find it more helpful to think about this in terms of the formula. So I'm expecting to see 10 divided by 3 to, well, the cube root of 3 would be 3 to the power 1/3 plus 1. And, oh, it turns out that 10 divided by quantity, the cube root of 3 plus 1, has a decimal expansion of 4.095, if you round up. So we found the critical value. Is the derivative of this function to the left of the critical value negative or positive? It is negative. I can check any of these values here. The derivative is negative. Is the derivative of this function to the right of the critical value negative or positive? It is positive. Again, I can check any of these values, and Desmos tells me what the value of the derivative will be for those. So in terms of a rough sketch of a picture, when the derivative is negative, the original function is decreasing, although not by a whole lot, because I noticed that the magnitude of these numbers is not very large. When the derivative of the function is positive, the original function is increasing. And again, not by very much, because I can see that the absolute values of these things are still like less than 0.1. So a very shallow slope, but a positive slope nonetheless. When I see a slope that decreases, and then it stops decreasing, even for a single point, and then it starts increasing, that is a minimum. And that is exactly what I'm looking for. So let's light up that graph of the original function. And, oh, there it is. I do have a local minimum. The x coordinate is exactly what I predicted it to be. So 4.095, or again, this was 10 divided by the cube root of 3 plus 1. So for my home decorating scheme, I should put the plant a certain distance away from that lamp. So some space here. So what was that fraction again? It was 10 divided by the cube root of 3 plus 1. I find that to be a more meaningful answer because I can tell why this number was important. I had to have cube roots in there because I'm trying to solve for the cubic being 0. That makes sense to me. Now, in terms of practical concerns, I don't have a ruler that measures in cube roots of a foot. So more practically, let's, round. So I can say, or by rounding, I want the plant approximately 4.095 feet from the lamp. So a little bit closer to the lamp than to the wall, but not all the way over on the lip. So, maybe about here. That's it. So I have found the best place to put my plant in my room just based off of building an equation to measure what I want and then using calculus to find the minimum possible light that this plant can receive, or whatever else my function is designed to measure.